So let's get going. I think Yuri sent a note saying he won't be able to attend, but he'll look or he'll listen to the recording. Anything people want to share? I don't see Gautam either. Dinesh, Steve, anyone else?
I'm afraid I haven't had a chance this week. I've just had other things on, so yeah, I haven't had a chance to look at it at all.
Dinesh, any luck with your
I
Siamese?
no, I never got the chance to get back to it. It's the same, like so many things going around in the workplace as well. So I never even got to run the old notebook yet.
Okay. So I did a couple of things, and I'll share probably starting. The first thing I'll just talk about before I start sharing the second thing, which is working off of what Steve did last week. The first thing I did was, unfortunately, I'd have to open a bunch of windows and waste time. So I'll just talk to it. If you recall, I had this two submissions earlier, that one of LSTM, which gave me about a 0.18 score, and one of CNNs, 1D CNNs of various sizes. So that idea, and somebody had already done it, but at least the same idea occurred to me as apparently did to that guy as well. But is, hey, what happens if I'm able somehow to combine this? So I generated a network which is a combination of outputs of the LSTM encoding, the CNN encoding, and I also did a time distributed, and I concatenated all three along with the leaks and sent that through a stacked layer. I didn't play too much with the parameters, which I might do this week, but make a long story short, I was expecting better results, but it gave me about same results as 0.18, 0.17. So it didn't really improve. I thought maybe because of the ensembling or no, it wasn't actually an ensemble because I didn't make the results. It's more I concatenated the encoding is the right way to say it. But that about gave me the same results. So nothing, so I could take you through that, but I will in a future lecture, whatever, if I'd already set up the notebook, but that's something else that I tried this week. I got it to work. The one interesting thing was I could not, for various TensorFlow reasons, get multitude of conventional outputs like con 1D, 2D, 3D, 4D. I couldn't do that. Instead, what I had to do was just take, say, a con 2D into a con 4D and then take that output and then just concatenate that with an LSTM encoding and time distributed encoding. So I'll share the details of that in a notebook subsequently, but at least the results weren't all that substantially better than just using the LSTM or just using the convolutional network. Now, with that said, what I did want to go into a little bit is the features of the network that Steve had used. So that's kind of interesting to me. So let me know when you can see my notebook.
Yeah, I can see it now.
Okay, so just to take you folks through. So this is the notebook I think that Steve had submitted with some minor modifications last week. I think he got the best score yet of 0.129 or something that low, or 0.13 or something like that. So figuratively, this is the network architecture of that notebook. Basically it's just an LSTM, and then the add multiply is something that we've looked at before, and then a bunch of concatenates, dropout, batch norm, introducing some noise, dense, dropout, bad norm, and then dense. So that's the extent of, it's not a very complicated network per se that he takes it through and gets a really excellent result. So given that we have already done the LSTM part and we're at 0.17, so at least I thought, hey, the benefit seems to be the features that he's using, which is what enables him to get from where, say, a couple of us are at 0.1718 to 0.1213. So I was interested in the features. So one set of features I can kind of fairly explain. And in the process, I learned a couple of modules in Python and stuff. But the other one, maybe we can collectively figure out, since I see Rekil, Mehul, Steve, if you are here as well. So without much more delay, let's look at he has 3 sets of features.
What are the 3 input layers, Srivastav? Can you remind?
Sorry, going back. Sorry.
Yeah, what are the 3 input layers? I see input layer 1, input layer 2. Why is there an input 3 there on the right hand side? Just what is being passed there?
I would have to check.
Okay, cool. Okay.
When we get to the notebook, we can look at it. I mean, ultimately, he's just using the 2 question 1, question 2. He might be doing something a little different with respect to taking only so many common words, blah, blah, blah,
Okay.
and passing that through. So when we look at that, when we look at his model, we can look at this.
Cool.
What's the third? These 2 I know are just the 2 Q1, Q2 questions. Yeah. This one is a little bit weird, but yeah, we'll look at it when we go through his model. Unless, Steve, you recall something off the top of your head.
I was just trying to remember. Yeah, so he has sort of the 2 halves. He has like your sort of standard, like looking at the question, but then he has like the leak thing, which is like sort of the ordering of questions and stuff, and he feeds that in as well. So like he has, yeah, so like there's the 2 Python files that you were just on there.
Yeah,
like
I'll take us through those 2, and then there is, so the thing I was looking at, and we'll get to answer your question, Rekil, in shortly after we go through the features. So he, surprisingly, as I mentioned in last week or last couple of weeks, we saw, this thing where people were using thousands of features. I mean, 1,600, 300, 500, blah, blah, blah. What's impressive also to me was he just uses 25 features, which is pretty small considering everything else. So I can well explain this 15. I will need help. I can, and we'll go through this 6. This 4 is part of the model, and I haven't looked at them yet because I just started on this a couple of days back. So this 15, I'll take you through. This 6, hopefully we can collectively figure out, because I have some good idea, but reading his code, I needed to play with it interactively, which I haven't done yet. And then we'll just kind of work our way through it. The 15 is first, let's look at, so he calls them, these first 4 are stuff that he uses in the model itself. So we'll deal with it last. This 15, he talks as it as NLP features, and then this 6 as non-NLP features, which is more like a factor of how you process. It's not a property of the strings in the questions. So that's why he calls them non-NLP, I think. So now let's start with the NLP features, which are interesting. So here, couple of things I kind of find interesting. We'll look at fuzzy wuzzy. Apparently, fuzzy wuzzy is a string processing capability in Python, from which you can import something called fuzz, and then that helps you find some ratios. We'll get to that in a minute. The other thing I found out is that apparently there is a distance module in Python that you can import as well, and that gives you various distances that you can easily compute. So those were things I learned, and we'll look at each of these modules and what they generate in a little bit as well, in a little more detail. So this replacement, it's just interesting, but you can, it's fairly simple. He's just replacing symbols. You can see he's replacing that with a rupee. This things he's just expanding won't to will not, in apostrophe T to not, blah, blah, blah. And then, replacing millions with 1M, 1K for thousands, and then sending back out the X. Now let's look at the more interesting 10 features that he generates using what he calls token features. So he sends, just creates a list. By the way, if this I just went through last night, so I'll talk to it. If I say something wrong and you can see some difference between what I'm saying and what the code actually does, feel free to speak up. This just creates a list of 10 values. And then, he just says, hey, if either of the questions doesn't exist or its length is 0, then, just return token features, which is nothing, list of 10 zeros. Interesting thing is he just creates words and stops by parsing or getting through the words if they are not in stop words, and then if they are in stop words. So Q1 stops are stop words in question Q1, and Q1 words are unique words in the question, right? So in question 1 and question 2, but because this is a set, it's a unique words. Then he just does common word count, and that's just the length of Q1 words intersection Q2 words. So
what are these stop words?
I think he has a list of stop words that he uses from this NLTK corpus, whatever he has as the step.
What is the definition, say, for a stop?
I used to remember this. Stop words typically are things like
most common words in any natural language.
Yeah, that's right. It's like is, the. So things like that which don't add too much to the meaning, but occur too often.
Cool. Yeah.
Yeah, that's what stop words are. And, you can define a list, and he's using the list that comes from the NLTK corpus, because different, like, what's the more recent library used for string processing that FastAI uses as well. I forget the name of it now, but that has different list of stop words than probably the NLTK does. So it's a library dependent list.
Cool.
So he counts stop words, and then he counts non-stop words. And then common word count is just length of the words in Q1 intersection with words in Q2, and then the length of that. And common word count, common stop count, and then common token count is just set of Q1 tokens. Remember that words, he has actually extracted the words in Q1 tokens that are not stop words. The tokens themselves are just the split. So there's a difference between Q1 words and Q1 tokens, because the Q1 tokens, the difference is that Q1 tokens are not a set, and it's the list of all the words split up in Q1. Whereas Q1 words is a set, so there's no duplicate, and it excludes the stop words. So that's the difference between this guy and that guy. And obviously stops is just the stop words, right? So that's why he does all three. Because Q1 tokens includes, and that's why he does the set of Q1 tokens, because Q1 tokens is not a set. And this is both stop and non-stop, whereas this is broken up into into non-stop first and then stops next. right? So he takes those three, and then it's very fascinating because look at all the features he generates. He generates 10 features, 0 through 9. So it's just the common word count divided by the minimum of the length. And safe div is just so that you don't divide by 0. So safe div is just 0.001, I think. He defines it up there. Here, safe div is, yeah, 0.0001. But anyway, it's just to ensure non-zero division. And so he just this min, max, then min and max of Q1 stops, min and max of Q1 words, min and max of Q1 tokens. So 6 of them are just this simple, let's just take the commonality and then divide by the min and the max, right? That's interesting. And then this one, I couldn't quite get the intuition for this. So if somebody can, I mean, I can understand Q1 token 0 equal Q2 token 0. That is, does int, and it just converts it to an int. But bottom line is, do the question start with the same word? And I guess this is, do the questions end with the same word? Now that I jump from here to here, I couldn't make sense when I went through this sequentially, but now that I explained it in reverse, it seems to make sense. So this just seems to compare the first word and the last word of the tokens is the same, then, you know, create a feature from that. And then the 8th one is absolute, just the difference of the lengths, and then the average of the lengths.
Is the last word getting split as a question mark if it's there, or are we kind of doing some pre-processing where we throw away the question marks? I'm just curious if you know at the top of your head anywhere there.
No, other than the replacements we can look at. Otherwise, I would imagine that the question mark, when you do a split, it won't split the question mark because there is, unless there's a gap between the word and the question mark. Do we typically write that way? Anyone recall whether there's a gap between the last word and question? I would think so, right?
Yeah, I also think there should be a gap. Otherwise,
yeah, if there is a gap, then it will show up as a separate thing.
last word from that. Cool. Okay.
And it's
if it shows up as a separate thing, does that, you know, like the test you just showed at number 8 there, the one that was like comparing the last token, does that mean that the last token is always going to be the same then? Oh, sorry, number 6.
Yeah, that's a good question. I haven't looked at it. Those are the things I haven't played with because I just looked at the code yet. It'd be interesting to play with it.
Yeah, I can't remember. There are question marks on there, yeah. So if it is treated as a separate token, then feature number 6 is always going to be true.
Yeah, if everything ends with a question mark. Yeah.
Yep.
The fact this exists would seem to suggest not, but it's something to look into. And I was thinking, Steve, that this first word thing may be helping him differentiate or help the algorithm differentiate between a what and a why or a where or a, you know, like what you were trying to do.
Yeah, exactly. Yeah. Yeah, because I think the first word is sort of a real sort of decider about what the question is actually asking.
Yeah. So this is an indirect way of conveying that information, right? Because if it's one, I mean, if they are equal, chances are it will indicate that it's a duplicate. Therefore, this is a good indication of whether it is or it isn't a duplicate. Or at least can help make the learning easier. So I thought that was kind of clever. And then these two are just the average and the difference. So I thought that's kind of cool that he does that length or does that 10 features, right? So 10 of the 15 are accounted for now. That is calls the NLP features. And they are understandable mostly. Right, and some interesting questions which we should look into of this last one, for example. Is it always the question mark? Then you come to get longest substring ratio. So,
Intuitively, what is 0 to 5 kind of pushing
trying
across?
to convey.
Right. Like if you were to put that in words.
Common words, but expressed as a ratio to the length of either question, normalized to lengths, so that, the normalization to length, you can apply the same logic as you don't want long or short to be adversely influencing it. The numerator would be how
Yeah,
much.
not really normalizing there, right? You're taking a min or a max. If you were adding both the word counts and then dividing it, then it would have been normalizing.
Yeah, that's true, but it's
Here, in fact, it's like if one question is smaller in number of words, you'll be bumping that number up really high. And vice versa, if one of the questions is very long, then you'll be bumping that number really down. So I don't know, intuitively, I don't know, kind of
that
lost.
is what it does to the common word count is, putting them side by side and figuring out. Again, I may be wrong, but intuitively I'd want to check whether my intuition says it's something like the number of common words in the two questions, in one, and there are two pieces to it. One, when the questions are short, or not, when you divide it by the, like you said, the shorter of the two questions and then the longer of the two questions.
Actually, now as you say, that kind of makes sense. So actually, feature 0 and feature 1 will be almost equal if both the questions have the same length, because then the min and max will give you the same value. The numerator is the same, you'll divide it by the same, almost the same number. So then those two will be equal. Whereas if Q1 or Q2 is small, then respectively one will become bigger and the other one will become smaller. At least mathematically that's what, but still
Right. So
intuitively I don't get
mathematically,
it.
that is what is happening. Now, how it helps us
Cool. Okay.
learn is the second level question, right?
Yeah. Okay. Yeah, I mean, like, why would I think of something like this? Is what is basically.
Yeah, no, I agree. In fact, I was about to say that, while they are understandable, um, exactly what you and I were looking at, even on the leaks, right? Like, how would we have come up with it, or why would we have come up with it?
Mhm.
That's still an interest. I can understand these two from that
I thought
angle
so,
a
yeah,
little
right.
better, right? Or
Yeah.
even the last two, because those are more like, if you know that the sum of two, or the divide, or the average of two, or the multiplication of two gives you better values, like we've seen, then that intuition leads you to the last two. And the intuition, I mean, which is still to be validated, of first words, and then, if the last isn't a question mark, does it help us differentiate? But
Mhm.
yeah, your question on these top six of why would we have come up with it is a good one. And that's where I think also, I mean, what I intend to do, but hopefully get to it, is kind of plot these features for the various questions in the data, and then look at what it tells you.
Yeah,
That's
importance towards the model also will be interesting.
right.
Which one's contributing? Yeah, cool.
Then these are 10. Now looking at get longest substring ratio. So what this is it uses the distance dot lc substrings, which is the longest count of the substrings. So, and then, he just says string 0 divided by minimum length of a or b plus 1. This plus 1 is just, again, to avoid, I think, the case where it's 0. But let's look at, I didn't, that's when I learned that there is a module. I thought distance was part of fuzzy wuzzy, but apparently it isn't. Let's see, where is this one? That's fuzzy wuzzy here. So this is the distance module, again, something you learn while playing with some of these things is you learn about new capabilities that exist in Python that I wasn't aware of. It's not basic Python, it's a distance module that exists. So let me go to this. So here is the guy's distance. So it's some set of utilities for comparing sequences. And it provides helpers for computing similarities between arbitrary sequences. So like Levenstein, Hamming, Jacquard, Sorensen, plus some bonuses. And this is a bonus. So now if you go to distance within this, and then look at LC substrings, which is what he's using, then you see what it does. Code is fairly simple. Basically, you find the longest common substring in the sequences. Okay, so simple example is here, LC substring, sedentar and dentist is you look at that guy to that guy is dent, and that's the longest substring which is common. And then when you do LC substrings and you say positions is true, what it says is it gives you the length of the longest common substring, and then it says this second tuple is just a tuple of the starting index for the first string and the starting index of the second string. So you can see 2 because it starts at 0, 1, 2, D, and 0 because D starts at 0. So it's length of dent, which is 4, and then 2, 0. That's all it is. So now back to our guy of what it does. So it seems from here, what he's doing is, obviously returning 0 when it's nothing. But if it is common, then he divides the length by the minimum of the length of A or B and then adds 1 just in case any of them is 0. Again, Rekil's question still applies of why would we do this, and would, if we had not already known that this distance module exists or the length of longest substrings ratio, what it conveys to us. Of course, you can generically argue that the longer the length of common substrings, the higher the probability of it being a duplicate. So from that point of view, it's not that irrational, but I wouldn't have gone to it since I didn't even know that something like this existed. Any comments? Okay. So this thing is just extracting the features here. So, he just applies the preprocess, which is cleanup or replacements, then fill NA, replace with null string, and then df question 1. So each of the questions, he cleans it up and then generates the features and sticks them in under these headings. So that's all he does in that piece of code. Now comes, so we remember he has already added 10 here, and the longest substring ratio is the 11th one, and then these 4, and we have accounted for 15 features. So let's look at what these features are. So these are what are called fuzzy features. So fuzzy wuzzy, as I told you, is this thing that is again a new module that's available, not new, new to me. So what is, can you guys still see my screen?
Yep.
Okay. So what is fuzzy wuzzy in Python? The library used for string matching. Again, something good to know. I hadn't heard of it before. So process of finding strings that match a given pattern, and it uses Levenshtein distance. So which begs the question, what is Levenshtein distance? So it's the distance between two words, which is the minimum number of single character edits. And what are single character edits? Insertion, deletion, substitutions. So it's almost like you start with a word, and how many single character insert, delete, substitutes do you need to do to get to the second word? That's the Levenshtein distance between two words. So we've learned that, and we've learned what is fuzzy wuzzy. Now let's look at an example of fuzzy wuzzy's ratios. So here is an example of fuzzy wuzzy ratios. So forget about the W ratio because we want this. Wait, let's see where was the, here. Okay. So first ratio, let's look at the partial ratio and the token set ratio, because those two are used by him as two of the ratio things. So he uses token set ratio and token sort ratio, right? And the third one, first partial ratio. So token set, token sort, partial. We'll come to this first ratio in a minute. So token set, token sort, and partial. So the partial, it says, if you look at Geeks for Geeks and Geeks for Geeks exclamation point, then the partial ratio is 100 exclamation mark, but still partially words are same, so score comes 100. And first partial ratio, Geeks for Geeks, and then Geeks, because there is for is missing, there, and it drops to 64 as opposed to these two guys. So the partial ratio is ratio of two things. And obviously you can go to the fuzzy wuzzy code and get the exact details of the code, but for our purposes right now, it just says, hey, what's the ratio of two strings common values, and what's the ratio of that? And the difference between now, let's say token set ratio and token sort ratio. So token sort ratio says Geeks for Geeks, for Geeks. It doesn't matter what the order is, because irrespective of order or position, it's the same. So it's 100. So token sort Geeks for Geeks and Geeks for Geeks, it drops because there is more, even though there is a redundancy here, but there's one more word. And so it gives you 88. Now compare that's the token sort ratio. Compare that to token set ratio. The word set says it eliminates duplicate, and so it gives you 100 even if there is a duplicate here. So the only difference between these two seems to be that one is a set and the other is a sort. And the partial says, if it's partially the same, then I'm going to give it 100. If things are missing, then I reduce the score. So that's largely, and then I think this first ratio is Geek for Geeks and Geeks. It's only 87, whereas it ignores capitals because these two gets, no, I take that back. It seems to give it 80 when there's a change in letters, when some things are capitalized. When it's exact match, then it's 100. And then it's an 87 because of this for appearing in these two. So it's just various ratios of parts of string appearing in other string. So I'll post, and then there's another post on fuzzy wuzzy and how to measure string distance on Python that I also found interesting because it gives a little bit better, more detail on how fuzzy wuzzy works on strings. Okay, so that brings us back to the NLP. So in effect, he just takes four fuzzy wuzzy ratios or four ratios from fuzzy wuzzy, which is string matching thing, one longest substring from distance, and then 10 of them this. So that combination of the 15 stuff is what he generates as and calls the NLP features. That's the 15 features that he refers to of the 25 that he uses. Any questions other than what we have already covered so far on the NLP features? Okay, so now this, I was on solid ground. Here I'll be in mushy ground because I didn't quite understand a lot of it, but just got a vague idea of what he was trying to do. Honestly, I think this is one where you really need to play with it, meaning need to see what the code is actually doing. But I thought it may still be worthwhile. People might have some intuition. Me struggling alone with it was not going to get me anywhere unless I actually played with the code. But so let's go through it fairly quickly because, as I said, the code is, or at least I wasn't able to decode all of it in my head about what the data, how the data is getting processed. But anyway, these are non-NLP features. So if I recall correctly, he generates, let's go down to the bottom and look at how many there are. So if 1, 2, 3, 4, 5, 6. So he generates 6 such non-NLP features, combines them with the 15 NLP features, and then 4 features he generates on the fly as he's building the model. So that's how he gets to 25. So let's look at these non-NLP features. So here, and right off the bat, I was kind of thrown off. Are any of you familiar with dstack already? Can talk to what it does?
No, seeing it for the first time.
Yeah, so I jumped to
Yeah, I don't know what dstack is, but like yeah, like a hash of the question is, yeah, like just creating a unique number based on the contents of the string. But
yeah, he actually creates a dictionary of that, which I'll come to in a minute. But dstack, turns out it stacked the arrays in sequence depth-wise, which he says along, and this is, I think, more a typical thing, along the third axis. So the arrays must have same shape along all but the third axis. And then you stack along it, I guess. So let's look at this here. So NP array 1, 2, 3. P is NP array 2, 3, 4. NP dstack A and B makes it 1, 2. So he's stacking 1, 2, 2, 3, 3, 4.
It's like a pairwise stacking. 1 and 2, and like just why would you do that?
1, 2. Yeah, I still don't get it, but
In general, do you guys have a way you look at these, when they have these brackets, like the 2 examples he shows there?
yeah.
Like when you look at it, like the first one is just a array, and the second one is a list of a list. I don't
No,
know.
he's just saying that this is, see, this one, the fact that there are 2 of these and then this, it stays, or even to make it simpler, if you look at this guy, this means that it's a column of, so this 2 or 1 square bracket, and within that a square bracket 1 square bracket 2 3 means that there's a column of 1 2 3 within this array. So it's an array with one entry 1, underneath it another entry 2, underneath it another entry 3.
I see.
It's a single column stack of values 1, 2, and 3, and this is again a single column stack of entries 2, 3, and 4. And then when you destack it, that means he's saying you, and I still fail to be able to explain what the destack does.
If you look at the shapes, it makes it easier. So from what I understand, what is happening is it's pretty much like the vertical stack. The only difference is, I think, you're adding in this third axis, right? Let me share this link.
Yeah, I'll stop sharing. Maybe you can do that. Let me stop sharing. Go for it.
Are you able to see my screen?
Yes.
Okay, so they start with something like this, which is 3 by 2, and B is also 3 by 2.
Right.
And then you end up with D stack of A with B, which actually turns out to be a 3 by 2 by 2.
3 by, so you're stacking 3 by 2. Stacking two 3 by 2s.
Right. So I'll hang on. Let's look at the where's the dimensions here. Okay. So I mean, so if you kind of just vaguely remember what the shapes on these are, this guy pulls out the shapes. So these are the two inputs: 3 by 2, 3 by 2. We know vertical stack, right?
Yeah, you just then it will become 6 by 2.
Exactly.
Right?
So hence it became 6 by 2. Then you have horizontal stack, which is going to place them side by side. So that's why it becomes 3 by 4.
Right.
D stack is adding in this third axis. And to look at what he says, if you want to put this out as explicitly, you can write it like this. So all it's doing is, this is your A, you're adding in this last dimension. So it became 3 by 2 by 1. Same thing with B, it became 3 by 2 by 1. And you're concatenating along the second, that is basically 0, 1, 2. So this is, you're concatenating along this last one. And that's what is giving you this 3 by 2 by 2.
So if you go back up to the how the result is, then let's check 3 by 2 by 2. So
if you want to count like that, that will be
1, 4, 7, 10. Yeah, got it. I see.
inside there.
Yeah, so you stack each of 0, 3, and 6, 9, because that will be your first, well, no, by 2 by 2.
0, 3, and 6, 9. That's what gives you this, like, if you break this down into 3 by 2 by 2, right? So this is the 3, right? 1, 2, 3. The leftover is 2 by 2, which is this section. There are 3 of these 2 by 2 sections. Does that make sense? So if you look at the shape, you end up with something like 3 by 2 by 2. So if you look at this innermost thing, this 2 by 2, there are 3 of these, 1, 2, and 3.
Yeah.
And then if you look at this 2 by 2, how it's broken is, you take that 0, 3 and you concatenate it with the 6.
But vertically? No, horizontally actually.
Yeah.
It is horizontal because you see that 0, 6, comma 3.
Right. That's what it's like that. Yeah. So I think, yeah, kind of.
Not an easy thing to visualize. You have to work it out for each dimension.
True.
Or each shape. unlike horizontal and vertical.
Yeah, that is pretty, yeah, easy to understand. This one is, yeah.
Interesting. Yeah, that's a good reference. You may want to post a link to that.
Yeah, I'll do that.
That's interesting. Okay, where was I? Oh, there. Okay. Okay, let me know when you can see my screen.
Yep.
Okay. So that's destack. Now let's go back to where we were. So you destack the question 1 and question 2, and then you flatten it. What it outputs, I really want to print it out. Can't visualize it yet. It does the same thing for test, and then it just appends the train and the test questions to form all questions, and drops them. And interestingly, he drops the duplicates from all questions. 0. That means I think if you are singling, basically he drops all duplicate questions, if I'm not mistaken, because he has stacked all the questions and then the train and test. And then if you drop the duplicate, that means you're dropping any duplicate between anything in train and anything in test. And he has already flattened the question 1, question 2. So that's my intuition, but that's why I said this one I might be waving my hands really fast because I haven't actually executed and printed out and stared at the outputs to really, which is what I would encourage everybody to do, to really grasp what's going on. And then he just resets the index, drops them. And then this one, I don't quite get what he's doing other than the fact he's converting it to a dict. And returning a dict. So even though he calls it a hash, he's actually returning a dict. Now, I still don't get what the keys and the values of the dict are. If somebody has an intuition for it, please speak up.
Isn't that 17th line pd.series is where you're kind of creating a data frame per se? So that's where you're kind of getting your keys and values, rows and columns?
Yeah, yes, that's true. I was saying, what are the keys and values? Here it seems all questions, index values are the keys, but
no, index
I'm not, the index may be the keys and the values are the values.
Yes, I think that's what it should be.
Yeah, but then index is just like plain simple numbering index, right?
What is all queues?
Because all queues is just the flattened dropping duplicates after you do this destack and appending the train and the
so
test.
does it give you a dictionary where the keys are the indexes and the values are the concatenated questions?
When you say concatenate, you're concatenating Q1 and Q2 is what you're thinking?
I think so, yeah. So like the first 2 lines are like lines 12 and 13. Yeah, like that's just taking question 1 and question 2, isn't it, from the training set and the test set, and sort of joining them together. And then you end up at line 14 where it's joins the training one and the test ones, drops the duplicates. Yes, so I think you end up like there, yeah, with a dictionary, which is just a set of indexes, and then the values are
concatenated
questions joined together. Yeah.
Okay. So as I said, that's where I want to execute and look at it and see what it's doing. But that's what you said, Steve, seems most probably what it is. So let's go with that as what the question dictates. Then he says get hash is you pass it a data frame and hash dict, and you will see later on that he's just passing in the question dict into the hash dict, and then creating the columns, which means df question one map hash dict. So no, so when you map a dict onto a column, what does it do? Would it just get you the value from the key? And if so, the question one should be the actual df question one would be the question itself, right? In which case it doesn't seem to, I mean, is it going from the value to the key or from the key to the value when you map hash dict? Because df question one, I would think, is the actual string of question one, correct?
I would think so, yeah. So I'm not sure how you would get it. I think, yeah, I think really you would need to sort of run the function to see.
Yeah, yeah. And then, return df drop. So again, that's why I said what I said earlier about, specifically what he's doing. And we'll look at it as we go down. It begins. So here he's just creating again a dict and calling it kcore, creating graphs from the question, adding edges from one question to the other, removing edges when the questions, I guess, are the same, so you don't have self loops. I again don't quite get what he's doing here.
Yeah, so I think all this stuff is what we were talking about last week, about like in all the discussion things about their leaks or whatever, where their leaks are really down to the ordering of questions in the data set, just how the data set itself has been generated. There was like a lot of people talking about how graph stuff could be used to sort of decide if a question was a real question or if it was one that was auto-generated to just fill out the data set. So that's what I thought that this whole sort of Python notebook was about, was basically sort of analyzing the questions in the data itself to sort of decide if they were real questions or if they were generated questions. And yeah, like the whole graphing thing was like a mechanism that people were talking about to sort of decide which question ordering applies.
Yeah. So, and then, what's, so as I keep repeating in order to really understand this particular notebook, I wanted to actually execute these pieces, the edges and what he does with the core features, as he calls them, and then how he sorts them, gets the neighboring features, gets frequency features, and then, for example, frequency upper bound he defines as 100, whereas neighbor upper bound is 5. And then he processes them using these. This is what is where he's actually using the functions that he's defined. So for example, when he says hashing the question, he actually takes create question hash, passes in train and test, and therefore gets a dictionary back that we talked about, which is, based on what we discussed, is an index and then a list of questions which may be concatenated q1 q2, which is the question dict. And then the get hash, he passes the question dict and the train df, and then gets a modified train df and a modified test df. And then this is much too consistent with our intuition. He says number of unique questions is just the length of the question dict. So, but if that's the length of the question dict, then I would think that there wouldn't be concatenation of Q1 and Q2. It would probably, but I could be wrong. It may be that unique, he just thinks is unique combination. So that's something to look into as well. And then calculating K core features, again, he uses the functions he has built to create the K core features and add them to the training and test DFs. Same thing with convert to min max, and then same thing with common neighbors. And so eventually and then this is a fascinating single line of code that I thought I should understand better because it is doing a lot of work. So if you see, what he's doing is vertically stacking these, right? And then I have to figure out what return counts equal true does, but then taking the unique values of all the stacked ones and then starting them, it means he's kind of exploding, or there's a different word for it. Whatever.
Unpacking.
Unpacking them. That's right. Thanks.
That
Unpacking them,
I
then
think that,
zipping them, and then converting it into a dict.
right. Where does that return counts true sit? Wasn't that with the NP unique?
Yes, because if you see, well, yeah, it is with NP unique, right? Because this parentheses
Is this not?
ends
Is this
with
not? Yeah. So like each question's got its own unique ID, and so yeah. So he's like sticking ID 1 and ID 2 together, and then finding out the unique one. And return counts. It returns you the count of how often that thing appears.
Yeah.
So if you've got question 1 and question 2, and yeah, like that appears 10 times, then return counts will say 10 for your data set.
and so NP unique will mean that it will only take one of the 10.
Yes, I think so. Yeah. So
Right.
yeah, so like if you've got 1 and 2, and it's in your test and training set 100 times, that'll return you 1 and 2 once, and then it'll count all the number in the return counts. And so your frequency map will show you how often question 1 and question 2 appear together. It'll give you a count of that for your whole training set and test set. I think
As
that's
a
what it's
dict.
doing.
As a dict.
Yes.
Yeah. Okay.
Yep.
Yeah. So I thought that was pretty cool. I mean, I'm familiar with the dict zip, but the fact that he combined it with stacking vertically and then getting the NP and then, unpacking it and then creating a dict all in one line. That's pretty cool. And then he just gets the frequency features this way and then adds these 6 features. Now, obviously, exactly what these features are, especially the min max score and the common neighbor ratio and count, is something that I can't yet explain and would like to play with to be able to give a better detailed explanation of that. But in order to do that, you have to execute the code and stare at the results, which I haven't done yet. But that's the additional 1, 2, 3, 4, 5, 6 features. So if you go back now, so remember we generated 15 NLP features. Now we have generated 6 non-NLP features, which at least I don't quite fully understand what they are, but we'll do some experiment next week to talk about it. So we got 21. And then to now, if we get into, and this is the part I haven't spent any time on, so let's see, where is, this is the model. So here Raquel would be possibly the answer to question. Since Steve has actually executed it, maybe if we stumble, he can help us out. But this is the actual model. And he's actually doing some lemmatizing of words, which I haven't seen. And then he does the pre-processing, which we have already seen. Parts of it actually does more here than just the first part. And then he gets the embedding, which is fairly standard for each word. And then does some numeric stuff. Just defines a function, then he prepares. Oh, with respect to this memento thing, before we just look at that, let me take you to what he says here, which I haven't quite grasped. Maybe Steve, you can help us with what he says here. So here's the model explanation, right, of what the model is. So he says questions are pre-processed at the different forms of writing. I'll try to be da-da-da-da. But this is the part which I thought was interesting, and I didn't quite understand what he's doing there.
Yeah, so I thought he was just using memento as a key. So basically, if the word doesn't occur 100 times in the training set, then it's considered to be rare. And rather than using, so it's just a token to represent what he considers to be a rare word.
Right, and
so as he says, it's irrelevant that it's called memento. That's just
right. That's just he likes, so he used that word. But so that means if it is less than 100, he replaces it with that with memento. Now, how then is he? So anything which occurs less than 100 times, and again, how this particular action of his interacts with stop words and stuff is something to figure out in the details. But anything less than 100 will become memento, right?
Yep.
And if he's then
so like that's just the same as if you have your whatever you call it, your dictionary in like when you tokenize normally, and
right.
you end up with like sort of the thing that's not in your dictionary is just given a key for being not in the dictionary.
Placeholder of whatever out of vocab.
Yeah.
Right, but
so
then
I thought it was just the same as that.
Question is this, Steve. Wouldn't, if you're doing this, then anytime the word is in the rare category, it's all replaced by memento, which means it'll all get tokenized as the same. So when you now compare strings and stuff, wouldn't they compare equal if these, because it's the same token? And wouldn't that lead to issues? That was my, at least my initial concern. Is that not the case, or there is some explanation which makes what I'm saying kind of not true? You follow what I'm asking?
I think it is. Yeah, but yeah, like that is basically just the same, isn't it? As like when your word is the word's not in the dictionary, like when it's like a noun or something. So I'm not sure, does he do something later to, like obviously if the question is something very rare or whatever, then you would think that those sort of rare words would be sort of key in deciding is the question the same. Does he do something after to take that into account? I don't know, sorry.
Okay, so what you're saying is it's just a more extreme case of dealing with out of vocabulary tokenization. More extreme in the sense that he's making anything less than 100 all the same, versus letting it figure out of vocabulary tokens.
It looks like that to me, but I haven't stepped into the code. So
okay, so that seems to make sense. So this thing, I think, is basically, that is what I believe, that where he replaces the stuff with the memento or new memento, or and to my question, it might be that he handles stop words and stuff differently. and then extracting the features, and then reading the train and test, applying it, creating the vocabulary of words which occurred more than min word occurrence. So that's the 100, I guess, that he talks about. Min word occurrence, yeah, yes, it has 100, and replace word is memento, embedding dimension 300, number of folds 10, batch size 1025. And he uses the glove word embeddings with 300 dimensions. And then he goes through vectorizer, count vectorizing. Oops. Min-bird occurrence, gets the embedding, training, tokenize, and then patch the sequences to the maximum length. I'm waiting to find out where we get to answer what Rekil had asked. And then, here is where the, he has the NLP features and the non-NLP features. He generates within this test queue features. Those are the 4 that are missing. So we should look at where they are. These are the 4 additional features he generates on the fly. And these, he calls them surplus in numbers, extracting features. I have not looked at it, so sorry, I can't explain even at a basic level what these are.
Sorry, what does his prepare function do? Because it's the one that generates surplus as its second parameter. Can we take a quick look at is that prepare? Oh, that's prepare just above there, isn't it?
Yeah.
Yeah, so that's the one that was doing the memento stuff.
Yeah, that's what I thought. But then it also generates the surplus in numbers from which he generates the features.
Yeah.
Right? Because so that's something worth looking into, of what 4 features he generates. See, because he just this features 4, these are the last 4 features that he generates right as part of the model in this code itself.
Yeah, so there in his function, so he's got his top words, which are words that occur more than 100. So if it's in the most common words, then it's not surplus. If it's not in the stop words. Yeah. I don't know. Yeah, so it looks as if it's just like sort of words that aren't sort of common or something, or surplus words.
Yeah. Somehow he seems to maybe extract from is numeric, and then there's numbers and surplus.
Yeah, so it's
what he uses here.
Yeah, so the surplus ones that are going to those 4 new features, they're words that aren't numeric.
Yeah.
And aren't sort of the top words.
Right here, intersection union. So this might be a way he's getting around what I was concerned about, maybe, that he's using the words which are not above 100, but which are common between Q1 and Q2 and which are not numeric, and using them somehow as part of features. Maybe.
Oh yeah, that's probably what it is. Yeah, so the surplus words would be the uncommon words, and yeah, like there he's like looking for the intersection and the union over the 2 questions for the uncommon words. So
yeah,
that probably is what he's after.
Yeah. So my, the concern I was expressing he addresses by doing this, probably. Because if those less than 100 times used words do determine and occur commonly between the 2 questions, he uses those as features. He reduces them to features. Interesting. Okay. At least we have a broad stroke of what he's doing there. But let's get to Rekil's questions answer, which is what is the third input? Is it just as features? Because the two are...
Yeah, it looks to be. So like his
Yeah.
LSTM, you'll put the 2 questions into that, won't you? And so yeah, so it looks as if the third input is just those
25.
25 features.
Yeah. You agree, Rekil?
Yeah, okay, makes sense. It's just kind of interesting that the input kind of passes through a couple of layers and then meets the features.
Yeah.
Like I've never seen that. Usually you always have them all kind of at that
Yeah, or
same
even...
input level,
Yeah.
right? Yeah.
Yeah, that's true, because he's
Interesting that he's passing it
like
through
that, takes it through LSTM to generate that, whereas this is the features that he has generated from this. And then it only combines or it here. The combination of the two
Right.
occurs here. Interesting. And then he introduces some noise, then drop out, done. But what is amazing is if you look at anything else, and he's like 24th in the top 10%, definitely, and stuff, and very close, 0.129 is 0.11 is kind of the best score. But the simplicity of this model compared to ensembling so many other things and stacking so many things and using XGB and neural network and is just phenomenal. Now, that said, I think the complexity has somewhat been shifted into the generation of the features.
Smartly generated features probably are then randomly.
Right.
Interesting.
So, yeah, I still would like to get the details of what we kind of hand waved through here, but I spent some time on it, so I thought I'd share to see how he's getting to where he's getting to.
I quickly drew out dstack. Share
Sure.
that.
I'll stop sharing so you can share that. Go ahead.
You guys able to see my screen?
Yeah, now.
Cool. So if you think of it in terms of the image, it's kind of the easiest. So this is like R, G, and B. And they're like 3x2s. A vertical stack basically would stack, this will be your R, this will be your G, and this will be your B. So that's why it kind of becomes like 9x2.
Yep.
Whereas dstack, what it's doing is, if you think of RGB, if someone had given it to you separately and you had to stack them up to make an image, you need to put R on top, G needs to go underneath that, and B needs to go underneath that. So that's where this extra dimension comes into play. So it becomes 3x2x1. And then you stack along this last axis, the one axis. So you're stacking them like a layer of pancakes, one over the other.
So it's almost like the channel axis in a sense.
Right. It is exactly the channel axis.
Yeah.
So when you index at, let's say, 0, and say give all values, you will basically get 3, 3, and 3, which basically is from the R, G, and the B. So that's what dstack that extracts, and that's why it kind of makes sense when you do np concatenate. We said you do np concatenate, you add this new axis for each of these channels, and then you concatenate along that last channel. So that's how you kind of form your 3-color image from individual channels. So I don't know, kind of maybe diagrammatically it helps to understand.
Yeah, no, the RGB diagram thing and stacking definitely gives the good intuition to think about it. If you go back to that and reason from there every time you encounter dstack, I think it'd be easier to
I guess,
visualize what is happening, which is the reason that NumPy also starts off by saying, hey, it's the, start it typically. I mean, you could, I guess, do it for any dimension. It doesn't have to be like the 3, but the 3 is what we are most familiar with. So it kind of
Yeah, I
appeals.
don't know. Like, I think, see, like, for example, I don't think VStack, DStack, and EdgeStack take that extra parameter on which axis, I think.
No, that's a default by the V and the H and stuff.
Right, exactly. So I think basically under the hood, all of these just use concatenate with that axis already specified.
Yeah.
Which axis you want to join them up with. Whereas the extra thing with DStack is that it adds this extra dimension and then concatenates that. Right.
Yeah. Interesting. Cool. So we learned D-stack and fuzzy wuzzy and distance and a few other feature generating capabilities today. So that's kind of what I spent some time doing last week, and hopefully be able to try more about getting a deeper understanding of what these features are doing, since at least the non-NLP ones and even probably the NLP ones, to gain what how they show up when, as Rekil was asking, how do they change, and then see. The one other thing I did want to do is, there's talk of this decomposable attention, much like the contrast loss, and I wanted to get a better understanding of what that is and how it helps, because that's referred to multiple times as a component of some of the better score gaining notebooks, not necessarily here, but even in the discussion. So that's something else. If people have time, I would encourage them to look at and share with the rest of us what they found out.
For this competition, did any of you create like a validation set and evaluate against that, was is always submitting to Kaggle and waiting for a score?
This, well, let Steve answer. My answer is this one was so quick that didn't, but if you look at, because it's almost less than a minute for it to spit out the answer. But that said, I think many of these notebooks do, like this guy, for example, uses tenfold cross validation to generate the results. So, and the test set is so, actually, even our training set is so huge that, yeah, it's trivial to create. Validation splits. So, Steve, Dinesh, you want to chime in what you folks were doing?
Well, I just ran this. Yeah, I didn't really check the sort of the validation scores, but yeah, so he's got like the two Python bits, the NLP features and the non-NLP features, and both of them, they take quite a while to process, but like it's obviously just creating the features for the whole set. Each of those took about an hour or something to run, but like once you've got that, then that's sort of, you can store that away and bring it back. In terms of the K folds or whatever, it took 2.5 hours to run all of that. But yeah, I didn't really look at the actual sort of validation scores from each fold.
Cool.
The one other thing, though, that I wanted to spend time on, because it's not clear to me, the understanding, at least my understanding, is still vague and confused about things, is this weight adjustment, or I forget what the terminology is exactly that we used, that really gave a boost to the scores. And using the ratio of duplicate to non-duplicate that's there in the test set as the weights, when you're training, adjustment of the weights, because Rekla, I heard you say in passing in one of the previous discussions that, well, I mean, that shouldn't be, or that shouldn't be the case, right? That doing that would not be appropriate, because you're using test information when you're training. but then I bookmarked something where just about everybody here does. All of these guys in the top, whatever, even 100, 200, have all done it. And so I started looking into that, and at least I have a bookmark thing I haven't read yet, but I just wanted to kind of bring it up so that if people are can spend some time and then be ready to discuss in an upcoming session. I bookmarked something which explained why it's okay to do that or it's acceptable to do that. I haven't read that blog, but it went into details of why that adjustment is appropriate.
Yeah, the only thing I think, if I remember correctly, the reason I said you can't do that is probably you don't have your test set. Right, what you're going to encounter in the wild is not something that you would pre-know. That was the only reason why I said that.
Yeah, no, that makes sense to me, which is the reason that I was curious that that would be okay. So I haven't yet read. So in, you know, so I'm kind of surprised, but that
Again, the Kaggle scenario, that is fine, right? Because you have a fixed test set, right? That's not going to change. So you can play around with that and I guess
but
tune
that's
it
what I
up.
was curious, and I'll look at it. Is it just that that's acceptable only when the test set is fixed? Because that would seem to be a narrow and not applicable when you do anything outside of Kaggle environment kind of situation, because your test set is never going to be fixed
Yep.
in the real world, right?
Right.
So in any non-Kaggle environment, that would not be accepted. And if so, then how or why is that knob even available?
I don't know. It's like kind of answering that question of how we weight losses, right? Like when you combine losses, you kind of weight one loss more than the other. And your kind of feedback metric is Kaggle's leaderboard, right? In
So
real
is it
life, you don't have a leaderboard when you're trying to submit.
right? Right. So is it just the case that when you suspect or when you have some other independent way to determine that the ratios you're likely to see in the real world are different from the ratios in your training set, then you provide a knob so you can tweak it to see whether it works better if the knob is turned, or is that it?
I think there are a couple of things here. I don't know. You should probably, yeah, you should share that article and you should see if the data set is imbalanced, we're talking of different things, right? You can always weight it so that data set will be
Yeah,
balanced.
yeah. And in this case, there is that element of imbalance, but imbalance itself is that's where the question arises. Yeah, I'll point to that in the Slack. But how would you know that there is imbalance if you weren't able to independently determine that your test set is somehow different from what you see in training?
But your test set there, the assumption is that is a reflection of your training set, right? So like if it's fraud detection, you know that it's your frauds are going to be less than 0.5% and 0.05%. So that imbalance, if you're talking of, you can counter that. That is fine, right? There's no per se looking into the future of that.
Yeah. So there, the point being that you have independent knowledge of your test set being different than your training set. Therefore, data skew being an issue. Not data skew, I should say imbalance, class imbalance.
Yeah, the class imbalance, right?
Yeah, yeah. Okay. Yeah, I'll point to that and would appreciate feedback or thoughts around that, because when that would be appropriate, I want it to be clear in my own head of when is it appropriate and when is it not to use that kind of adjustment. Okay, I'll post the link to that. I have it bookmarked. I just need to find it. Okay, any other comments or thoughts, folks? If not, thanks for joining, and let's kind of keep pushing 1 or 2 more weeks on this before we look at other problems. Great. Thanks, everybody.
Okay, cheers. See you next week.
Bye.